All right. So we still need to get through all of this. I'm gonna leave the bounties the way they are. I'm pretty confident at this point that nobody's gonna find a 3-axis accelerometer with a easy to use package, but I'm gonna leave that up there just because you never know. And all right, so last time we were trying to decide how we were going to do all the pinouts for the Teensy because there was a lot of stuff going on. So it looks like, actually, one thing I want to check real quick. So I think I decided last time, or realized last time, that the New Haven display was an SPI communication, not I2C. But I need to double check that and relabel it on this chart because otherwise I'm going to confuse myself. So I just need to find the data sheet. Here it is. And then, yep, SPI. Okay. Sounds good. So let me change that here. All right, that means that certain probably pieces of that I've already worked out, but I need to keep that in mind. So I think the TNC only has two SPIs, two different SPI buses, and obviously we need three of them, right? We have SPI for the LCD screen, we have one for the accelerometer, and one for the other accelerometer. Because the screen is not being used that much and only being occasionally updated, and when it is being updated, it's not, the accelerometers are not going to be in use. We can actually share this one, SPI one, between the screen and the accelerometer, and we'll use different chip select lines to turn them on and off. So, and that is one of the awesome pieces of SPI, is that it can just you can use it to connect multiple things that way and use different chip select lines to turn them on and off. Now, the one thing to note with that is that you can only have a single master device, something controlling those control lines. All right, let's jump back into this. So we got the NeoPixels last time. So this is where we're going to start today, was with these accelerometers. All right, let me pull up my chart here. And we're just working our way around the Teensy. Oh, I need to pull up the Teensy chart. Okay. I think I downloaded these last time. Here we go. So just working something out here. Okay, here it is. So this is what we're using. We've gotten close on, let's see, where we at? 36. So we've worked our way around this side and working our way up all of these lines. So good to know. All right. Also, let me know how your Thursday was. If anybody has anything interesting to report. I might have to change how this spreadsheet looks. All right. I guess first things first, I need to pull up that part and see what exactly the pinout is and everything. All right. Adafruit. What is this one? 2809. Triple axis accelerometer. Both I2C and SPI interface options. Okay. So here it is. I gotta figure out exactly how this thing gets wired up. Okay. Pinouts. This should use 3 volts DC. We've included a voltage regulator board that will take 3 down to power the board. Give it the same power as the logic level of your micro. Okay, so use 3 volts to 3 volt from the voltage regulator. You can grab up to 100 milliamps from this if you like. Common ground. I2C pins, SPI pins. SCL is the clock, SDA is the data in, SDO is the data out. So Mosey, MISO, and then CS is the chip select. These aren't labeled though, are they? Oh, they are. Okay. Cool. Ten. Okay. Sorry, I'm just looking at this chart over here. Trying to make sure I have everything. I understand everything. All right. This one. Okay. So first things first, so we don't have to worry about the power. I don't care about that one. I care about Mosey, MISO, clock, and chip select. So I believe SCL is the clock, and that should be first. All right, and this, sorry, part number, Adafruit 2809. Okay, so SCL, the clock. I pull up my teensy diagram. And this should be SCK, which is going to be on the LED line. I remember thinking that was weird. So it's pin 13, which we've already used, but we're also going to use for this. We're going to share it. So I guess I am going to need to copy this. Since we can have multiple devices on one line. All right, and the device is the Adafruit 2809. And we're going to say that this is 0, the first accelerometer. It is the 2809, right? Yep. No matter how many times I read it, I'm still going to forget that number. Okay. Let me pull this up again. All right, so that is the clock, 2809, and this is SCL, the SCL pin. These aren't numbered, so we're going to have to go with naming. All right, nothing to worry about note-wise on that. All right, the next thing is SDA, serial data in, sensor pin for the data sent from your processor to the device. So that's master out slave in Mosey. Excuse me. So Mosey is pin 11. Yep. There it is. And we said that was SDA. All right, so the other thing to note, even though the screen uses this chip select pin, we're going to have to use a different one for this device. Otherwise, we won't be able to use them on the same SPI. So we got to find another one. How about pin 36? I don't think that's used for anything right now. Oops. Oh, we haven't been naming our signals. Emitter 0 CS. Okay. That looks good. And then pin 38. Or, no, I don't need to worry about that. Okay. What's next? So that's chip select, and then we need serial data out, so MISO, and that should be the same as the other one. Where is it? Oh, we probably didn't use it on the display because that doesn't actually ever send data back. So I'll have to find it. So pin 12. We said it's not connected, but we're going to change that. All right, and that's SDO on this device. Where'd that go? There it is. Okay. And this Adafruit device. Excellent. All right. You know, something I didn't check is what the data level was for the screen. 0.8 times VDD. What's VDD? Is it 5 volts? Plus 3 volts. Okay, it's 3 volts. Good. I didn't think to check that. A lot of displays run on 5 volts, and that was going to be really bad if we had to. I mean, we could have done it. We just had to do it with some level shifting, but. All right. So I think that's the entire first one done. Now we need to do the second one. And so all of that is going to be on SPI 1 on the device. So that'll be, this is the chip select. I'm just looking at, going off the sheet here. Okay. And then MISO 1 is the next pin. And what does MISO go to? SDO. I guess I can merge these. Okay. All right. There's MISO, and then Mosey is 26. And that will be SDA. And then I think the next one is the clock, so we'll combine these. Okay, I think that's everything. And this will be SCL, yeah. Okay, so those are our 2 accelerometers done. Now the motor. I guess for the motor, we haven't fully decided exactly what we're doing yet. We said we were going to use this motor. I'm wondering if we shouldn't wire it up for like 2 of them just in case. Like we have the extra IO, I think, so we should use 2 motors. I mean, we can only use, at the end of the day, we may just use 1. And that's, I think, the current plan with how big it is. But if we decide to switch and go to a different motor or something, we can go to, we could use 2 of them. I think this thing could drive even up to 4, so I'm going to have to look this chip up and learn some stuff again real quick. L293NE. Okay. Get to look at the data sheet again. Here, I'll pull this up so everyone can see it. Okay. Yeah. Drivers. Electric relay drivers. Need to find the application circuit. I remember it being in here. Some measurement stuff. Okay. Should we be able to control them separately? Or wait, I think that's fine anyway. The way that I have to, okay, hold on. I remember reading this wrong the first time. So where's the pin out? Here it is. So basically, the enable line just enables the channels, turns them on effectively. And then the driver outputs are the Y's, and then the A are the driver inputs, non-inverting. And then you supply 5 volts for the logic, and then supply 4.5 to 36 volts for the actual drive. So what we need to do is put both of them on one side. Because of the way the enable line works, we need to be able to turn them on and off with a single line. So enable 1 and 2 at the same time. So attach one motor to 1 and one motor to 2. And then, yeah. I wonder if it's worth just doing all of it, just because. I don't foresee us using like 4 motors, but it'd be kind of cool, I guess, to have that extra power to be able to turn on and off. Oh, that's true. We can turn the power on and off really for high-powered items. It could be a good way to turn on and off the NeoPixels. Depending on what this thing can drive, current-wise. Peak output current, 2 amps, 1.2 amps. Ooh, I don't think that'll be enough. We might just have to drive the NeoPixels directly. Yeah, I think that's what's going to have to happen. But maybe we still leave them anyway. Current's 1 amp. It could be good for doing things like turning a screen on and off or accelerometers maybe. Yeah, I'm going to wire them up anyway. Just in case, because you never know. And we can always just disable them. So that basically means we need one control line to go to the enable on each side, and then a line to each of the A, 1A, 2A, 3A, 4A. Where 1A and 2A are going to be the motors, and then the others are going to be the auxiliary. So is there anything else important? We have USB. That goes to something different. I think everything else is just standard GPIO. There's nothing special. So yeah, nothing special, so we can just use whatever's left here. Use some of this generic I on the other side that's not being touched right now. I'm going to leave the I2C stuff blank if I can. That's pins. Well, the ones we haven't used. Well, actually, I don't know if it matters much. We use 24 and 25. Yeah. It'd be nice to leave an I2C bus just in case. Yeah, I'm gonna leave the. Oh yeah, okay. There is a bus free. So pins 16 through 19 are gonna be just left blank, just in case we have to add something else. So I'm gonna specify those as. Let's see, I2C, SDA, SCL1. We might just break them out to a port on the board or something. This one's SDA1. And then we have, oh, it's backwards. Okay, and then from that last thing, we decided we needed, for that motor, 6 lines. So we're going to say this one is going to be the motor enable. And then we're going to say motor 1 and motor 2. And then aux enable, aux 1, aux 2. Man, it is a good thing we used the Teensy 4.1 and not just the 4, because look at this. We have used up almost the entirety of the I.O. We wouldn't have had enough pins if we had used a smaller one. This is going to be an amazing schematic to do. And there's going to be so many parts on this board. It's going to be great. Okay. So now we need to assign these to the device. L293NE. 293NE. And we will merge all these together. Where'd it go? There it is. Move this over to the other side. So pin 1 for the motor enable. Thankfully I can number these. Let's see. For motor 1 is 2. Motor 2 is 7. And then the auxiliary enable is 9. Aux 1 is 10. And aux 2 is 15. Almost there. All right, so that's the motors. Okay, and then we need to do what's next? I should just look at this. The recharge circuit. Oh no, USB data. Actually, this is probably more important right now. Okay, USB-C port, Molex, this thing. Let's just copy that number and get that connector. And figure out how we're gonna, and we know that our USB data is this one. And I don't know that we totally figured out how we're going to connect it yet. Okay. Oh, excuse me. Trying to hang in there. I'm tired. USB data. All right, so I'm looking for the backside of this. Yep, here we go. So basically, yeah, our USB stuff is here. D minus D plus. Voltage USB. Got to separate VN from VSB if using external power. I remember reading that. I remember looking at this and thinking this is going to be so difficult. Oh yeah, we were going to put holes underneath here with pins that went through to solder to vias, and then we were going to also put vias out here so we could use a connector if we wanted to. So we just need D- and D+. And that needs to be connected to this USB port. Which I have pulled up here. And then I think the specification says which one is supposed to be what. Let's see. I remember this reading about this. Here it is. So you have to connect D+ to A6 and D- to A7. Okay. So D+ goes to A6. That goes A7. And then the 5 volts is obviously voltage of the bus. I don't think I used that. Okay, yeah. And then in our drawing, we need to verify that that's what those pins are called. Looking for a pinout or something. Here it is. A1, A4, A5, A6, A7. Okay, that was really hard to see with that line, but that's a A6, A7. I think the big ones are usually grounded. V bus is A4. Okay, cool. A4 and B9 are both. So I should probably connect both. They're probably opposites of each other, right? A4 and B9. Oh, and A9 and B4. Okay. So all those pins need to be connected to the voltage bus. So instead we'll say A4, A9, B4, B9. And then our part is this Molex part. Copy that. And then we'll merge all these. All right. Okay, so that should be all of our USB stuff done. And then obviously the voltage of the bus there will also go into charge to our charging circuit. All right, excellent. What's next? Then in the recharge circuit, we have a signal line for this part, which I believe is the charging manager. Yeah, so USB-C, voltage boost, and then this. Advanced linear charge thingy. we're going to do a dual cell. So ours is the 8.4 volt version. All right, let me pull this up on screen too. I believe it's the status line. We need to double check which part we're working with here. Oh wow, I have so many tabs open now. I don't need that one. Probably don't need these ones either anymore. Okay. So it's the WSN-TR 2057 WSN-TR 7 WSN, which is the SOIC package. ESSCC. So what's our pinout description? Voltage sense input, charge control output, charge rate compensation input, current sense input, charge status output, temperature sense input. So just this one, the charge status output is the only one we really care about. So that's going to have to go to just some pin. So that's pin 5. How about 20? I think, well, actually, we should double check that. Is pin 20 a... Pin 20, it is. Okay, so useful feature. It is an analog. So worst case scenario, we can, if it turns out to be an analog, I think it's a digital pin, but if it turns out to be an analog, this works just as well. Okay, where'd that go? There it is. Charge status, we said this is pin 5. And our device is this one again. Okay. And then we need to double check how exactly this works. And it's a voltage level. So output low is 0.7 volts. Output high is VCC minus 0.05, which I think VCC is going to be 5 volts in this. Yeah, it's going to be 5 volts. So this is going to be a 5 volt output. So we have to do this. The best way to do this is going to be through a voltage divider. Okay. And then the status pin. So that's something you can like put to an LED or something. I guess it's just, if it's going to an LED, it must be a discrete logic. It must not be analog, so. Status equals low. Okay, yeah, it is definitely digital. I guess we gotta decide if we want to put an LED on it or something too. I don't know that that's really necessary. I wonder if there's a way to know if this thing is charging though. That would be kind of cool. I don't know that there really is a way. Oh, it's a 3-state. Charge status output. 3-state. How does that work then? Indication of charge in progress, charge complete, and temperature fault or sleep mode. So, or basically not running. Man, we're going to have to come up with an epic state machine to make all this work. In the code, at least. All right. So how does this work? Charger using a P-channel MOSFET. This is going to be a great circuit to do. All these resistors and everything. Interesting. Don't need that. Okay. Oh, interesting. Okay, they're using 2 pins. Why? LED, dual chip LEDs, or for the interface to a host or system processor. The user can use an output port as shown in figure 11 to recognize the high Z state of the stat pin. In this configuration, the user needs to read the input pin, toggle the output port, and read the status pin again. Oh, okay, that makes sense. I guess the input port always matches the signal level to the output port. So basically, you're just running kind of its own pull-up. Oh shoot, we may not even need an extra pin and processor there. We could possibly use the internal pull-up for that. But basically, the status is either going to be high or low if it's in the middle of doing something. If the battery is charging, it's going to be high. If the charge is complete, it's going to be low. And if it's not doing anything, basically it's in sleep mode or something, as if it's like unplugged or something, or no voltage coming in, then it's going to go into high impedance mode. In which case you could toggle this output pin, which is safe to do because it's behind this pull-up, and if this line changes with it, then you know that it's in that mode. So it takes some programming, some processing to do that, but you can detect it. So how does that work? If it's low and the charge is complete, if we see it go low and then we toggle our output high, we'll see it. Okay. I just need to think about like what happens when it gets unplugged. Basically, if that stat changes, then we know to check for things. Yeah, we can make this work. I don't know if I can use the internal pull-up. I'm not sure exactly what the... Well, we need to know actually what the resistors are on the high impedance state, which means checking our specs again. And I don't know if it's gonna... It may not have it in here. I would think it would, but... Looking for something, and then with ohms. I don't see anything. That's disappointing. I wonder if there's anything more at the end here. Packaging, yeah, no more characteristics. Okay, so we're going to do that external pull-up idea. Does it say what value of resistor to use? All right, let's pull up. If VCC falls below the voltage at the bat pin. Right, so if the voltage goes lower than the battery. Yeah, it doesn't look like there's anything saying what resistor value to use there. We're going to use something kind of low. Maybe like 1 or 2K. Alright, so we need 2 pins. Basically, we need... so I said charge status. I really need it to be a charge status in and a charge status out. And that's going to go to pin 5, so we don't need to worry about it there, but we need to... Did through 1K ohm. Okay. I think we figured out most of our... I think we figured out everything. All of the pins on the teensy that have to be used. This circuit is going to get very complicated once we add all the other stuff in as well. I think we said our power button went to that on-off line, right? Yep. Power button in. So I guess that'll be the next step, is actually making the circuit. In order to do this, we're going to have to probably do a lot of 3D models of parts as well. Because I don't expect Circuit Maker to have all this stuff in it. It just won't. And then, man, this is going to be a complex board. We might do a 4-layer board. Even though it's more expensive, it's not that much more expensive. And it might be worth it for this scenario. Okay. Is there anything else we need to do right now or understand how to do? I think we're okay. You know, I'm a little worried about this, honestly. This USB device thing, getting it wrong. I'm wondering if we shouldn't connect. So, let me look this up again. Let me just double check here. I think we're okay. I'm worried about, like, cause with the whole USB thing, you can plug it, or the USB-C, you can plug it in backwards. And if the DN2, DP2 thing will cause any issues there. I'm wondering if I shouldn't connect B7 and B6 as well, and like do everything through jumpers, so that we can add or remove them as necessary to make this work. That might be a good idea. So B7 and B6. And then let's merge these. Connect all separately. Connect all of them separately through a 0-ohm jumper. Okay. This will give us basically some room to mess up. What this concept is, effectively you can buy resistors that have no resistance, so they're really just wires. And the reason for doing that is if you want to do stuff like this, where you want to lay out different lines in your circuit board but only connect one at a time, you leave spaces where you can solder a resistor, and then you solder these on anything you want to actually connect, and anything you don't want to connect, you just don't solder them on. And it's an easy way to change things on the fly, or do something like this where you're trying to specify like certain things connected but not others. So that's what we will do there. Okay. I think we're good to go. I think we got everything. The NeoPixel stuff. I might change this, honestly. We have to, right now, we have to do our own, we have to write our own NeoPixel library to do this, but there is a library for the Teensy 4 that uses a bunch of the pins. Hold on. T4.1 NeoPixel. Yeah, the Octo library. Okay, on the 4.1, there's 8 different pins that can be used for this library. 2, 14, 7, 8, 6, 20, 21, and 5. Basically, none of the ones that we've used already. 9's not an option. 15, is that an option? Nope. 22, 23, no. 21 is, and 20. Okay, here's what we're going to do. We're going to move this down to here. And then we are going to connect 20 and 21 as our NeoPixel pins, which we don't have to use. We can write our own library, and we're going to try and do. But if that ends up not working out or we need to do it quickly, we can use the built-in library. And here it is right here. 20, 21. So this just protects us again, or gives us more options down the road. All right. At the end of the day, 1, 2, 3, 4 unused pins. This is probably going to be, honestly, the most complex circuit I've ever made. I worked on one a while back, which was pretty difficult, but I don't, well, maybe that one was more. It used a 144 pin micro, so, or 100 pin micro actually. But I know we didn't use near all the pins. Yeah, this might top the list. I think it's definitely gonna have to be a 4-layer board. Honestly, if the Teensy wasn't so easy to program, I would seriously consider doing my own micro and just picking something. But in this case, I think we're going to be using the Teensy. All right. So that's sorted out. I guess next thing's next is we have to start figuring out what we're going to do in Circuit Maker to make all this work. I didn't really want to get into that tonight, but I figured this would take longer than it did because it took so long last time. But I guess not. I guess it wasn't that hard. I'm wondering about our power button situation, actually. Nah, we leave that as is. I think. I'm actually another thing. Our voltage regulator. I wonder if that has an enable and if we turn that off, if the teensy is off. No, I think we need it still though because we need to supply power to the teensy. All right, this is that whole power issue we were getting into last time and I got really confused over, but I really want to go through it again because I don't understand quite how this power button works. Let's see here. I'll show you all what I'm thinking or why this is confusing to me. There is a power. Okay, here it is. On-off pin and power control. A special low power state which turns the 3.3 volt power, which turns off the 3.3 volt, can be controlled by the on-off pin. A push button is meant to connect it between the on-off and ground. While running, hold the button for 4 seconds to turn off the power. Pressing for 0.5 seconds while power is off turns the back on and reboots the processor. If a coin cell is connected to BVAT, the power state is retained when main power is disconnected. Now BVAT, the power state always defaults to 3.3 volts power on, even if the on-off button had been used to turn on the 4VN. It's removed. That I don't care about, but what I do care about is I don't understand if we're turning off the 3.3 volts. I gotta look at the schematic again for the teensy. I apologize for getting hung up on this, and I know this may not be the most interesting thing, but it's really important for this project to understand how this works. So I need to look at the schematic again here. Okay, so it's way down. Here it is. Okay. So our on-off, this is the part that confuses me. It goes directly into the processor. And then our enable line, BMSC on request. Let me look this up, actually. Maybe I can find the datasheet on it that'll explain it. X2 DVJ6A. I can tell you right now that based on how powerful this thing is, this is going to be a really complex datasheet. $117 pages for the initial data sheet. I believe it's an ARM core, so yep, an M7 ARM core, geez. So basically, this will have the overview stuff, and if we need info on anything specific, we might have to go to a different document. I want to see if this has anything about the power on-off stuff. Or if it has any kind of pinout that might tell us that. Nothing there. Special signal. There's clock, Xtel. Connected. On off. On off can be configured in debounce. Off to on time and max time configuration. Generate debounce is used to generate the power off interrupt. While in the on state, if the on off button is pressed longer than the debounce time, the power off interrupt is generated. On time supports the time it takes to the stable transition from off to on. Max time configuration for 5, 10, 15 seconds and disable. So this is that pin. But I still don't quite understand. Maybe I should tweet the guy that made this and see what he says. Let's see if there's anything else in this document regarding that. On-off is M6. These are just all the pinouts. Okay. What was the other pin called? The one that controlled the PMIC on request. Hold on. Let me look at the other N6. Where is that? USB V bus. Maybe it gets powered through that. PMIC on request. Okay. Well, it could work. It's just kind of odd. And what's this regulator? ELV. I think I've looked this up before. Yep. Low dropout regulator. Enable. So it has this enable line. So how does this enable line work? Does it have a voltage level limit? Drive enable greater than V high to turn on regulator. Drive in less than V low to place the LDO into shutdown mode. Max is 6. Okay, so it could be a 5 volt thing. Had it listed. What was it again? V low and V high. Oh. 0.3 volts. Okay. And V high minimum is 1 volt. Okay. So that's interesting. I'm wondering, so the reason I'm looking into this is now I'm wondering if I can use this same interrupt, the same pin. Actually, I don't even know if it's brought out. I don't think I can. I may not be able to. Yeah, no, it's not even, never mind. It's not even brought out. It'd be cool if it was, because I was thinking about using it to control my 5 volt regulator. But I guess not. So Oh, now I'm curious though. If my 5-volt regulator has the one that I picked out, I'm pretty sure it has an enable line. I just wonder if it could have worked on this. What was it? Oh, here it is. This one. Because we needed something that could do like 5 amps. For NeoPixel reasons. All right, let's get the data sheet here. Oh man, which one did we get again? 29501. 501. This one. A version of this one. Where did all these windows come from? I'm terrible at doing this. 29501. 501 is this pack. 5 lead. We have an in, ground, out, flag, and enable. So what do the flag and enable lines do? Error flag signals output out of regulation. All right, let's go around current. Got to figure out how the enable works as well. You'd think it would tell us if it was enable high or low. Enable 0.3 volts to V in. It's voltage. Input logic voltage low. Voltage high. Enable pin current. Current and shutdown. 500 microamps. Interesting. Okay. Yeah, we can't do it anyway. So it could be possible to do, but there's not really a way to do it because we don't break the pin out correctly off the teensy. But we could, turn this regulator on with that as well. Although I think I think she think we couldn't do that anyway because our teensy, we'll be turning off the 5 volts. It's coming into the USB V-bus thing here, which would basically leave the chip in an unknown state. Yeah, that would be kind of weird. That would not be good, basically. So, yeah, that can't work. Okay, well, it was a good thought. Yeah. So I guess our circuit is probably done, assuming that my understanding of this is correct, the whole power thing. I'm wondering, maybe that should go through a jumper into a pin as well, just in case. Yeah, I'm going to do that just to be safe, in case this doesn't work. This is the part where we have the extra I/O, so I'm just deciding if there's anything that we could possibly use to just make this a little safer. All right, so power button in. Zero. And we'll just put this on a digital pin as well. How about this one? All right, we'll say connect through 0 jumper. And we'll say that for this one as well. Just in case it doesn't work like we think it does. All right. Man, there's just going to be so much software to write here. I'm just looking at all this different stuff. Oh, man. I cannot wait to mess around with this. But yeah, this is going to be a lot. Okay. So I guess next thing's next is we got to start making the circuit. And so path going forward, I want to design the circuit, get everything laid out so there's plenty of time to go back and look at things, review, whatnot, because it is going to be very complex. And then I want to start actually doing the physical design of the hilt itself and of the lightsaber, because that's going to determine the shape of our board, how everything fits in there, and that is going to determine a lot how we lay out the board, the shape and whatnot. So we don't want to lay it out beforehand, because obviously then we'll have to work the entire hilt around it, and that'll be very complicated. So we want to do the physical design next, decide how much space we have for the circuit board, pack everything as tightly as we can, and then once we have the full amount of space, we go through and actually design the board and lay it out. And then once that's done and we have an idea where everything's going to land and how it's all going to work, then we can write the software and decide too if we need to order parts and test them, or if we just order the board and put it all on and hope for the best. That could be an expensive option, but also the most fun. So yeah. So do I start the schematic tonight? I think this is good prep work. I think this is a good place to stop and commit the project and get everything up there on the GitHub, so anybody that wants to can kind of look at it and do an overview and get an idea of what's going on and maybe point things out. And then next time start the schematic. Assuming I'm not finishing up the MIDI controller as well. So I think I'm going to do that. So thank you all for joining me tonight. I really appreciate your time, and those of you for watching, thank you so much. I will be back on Tuesday, and we will continue either laying out the schematic, or I will be cutting up some plastic so that we can finish the MIDI controller build. Hopefully that second option, honestly. I really want to get that done so that we can move on with this. All right. You all have a good Thursday. I will see you next time. Bye.